your answer. Okay, so here for number 2, we no longer have one object, we have more than one. So if object 1 has kinetic energy EK 1 and object 2 has kinetic energy EK 2, the question is, can the total momentum, so that's the total kinetic energy, which is not 0, can the total momentum P1 plus P2 be 0? And of course, as you can guess already, I'm sure you're screaming your lungs off. The answer is yes. Okay, so how does this work? If we have the two balls moving either towards each other or the two balls are moving away from each other. So as long as they move in opposite directions, and not just that, the added feature is the momentum. If the momentum of 1 is P, then the momentum of 2 has to be P as well. So here you can see that this is just P, it's a plus, so let's choose that direction as positive. It's plus P, then this one is moving in the opposite direction, so it's minus P. So then the total momentum is the sum of the two, so we get 0. And even here, if I have momentum P for 1, which is plus P, if I choose that as positive, then this one is minus P. So the sum is just P plus minus P, which is 0. But just a reminder, P is mv, so we do have non-zero V. So that means we have non-zero kinetic energy, so we'll have 1/2 mv1 squared plus 1/2 mv2 squared. Okay, so even though we have 0 momentum, we have non-zero kinetic energy because this term is positive, that term is positive, so the total answer is non-zero. So the answer for number 2 is a definite yes. Okay, so now number 3, we have a 0.5 kilogram ball which is dropped from rest at a point of 1.2 meters above the floor, and the ball rebounds straight upward to a height of 0.7. What are the magnitude and direction of the impulse of the net force applied to the ball during the collision with the floor? Okay, so now let's look at number 3. Okay, so number 3, we are told we have a ball. Let's assume it's a tennis ball. Initially, it has a height of 1.2. It's dropped, so if it's dropped, that means the initial speed is equals to 0, and then it bounces off and it comes back to a smaller height, which is 0.7 meters. Okay, so now the question is, what is the impulse? Okay, so the impulse, we said, is the change in momentum, or it's also given by the applied force multiplied by the change in time. Okay, so the applied force would be the force of the floor on the ball. But how does this work? What is this T and where does it come from? When the ball is in contact with the surface, it deforms. So it deforms and then it gains kinetic energy in the opposite direction. So initially it's coming in and then it's deformed and then it's pushed up, and that's how it works. Then it gains the shape back, and this part where it's deformed, it's in contact with the surface, and it takes a time t to lose contact with the surface. So it experiences a force F during that time. Okay, so that's the impulse. But in this case, we don't have the force and we don't have the time, so we just need to calculate the change in momentum. So how do we then calculate the change in momentum? The momentum that it has as it hits the surface, that's our initial momentum. So we need the final speed as it hits the surface for this part. So here we need Vf, and that Vf is our initial for the total problem. So it's the final for this section, but it's the initial for the change in momentum. Okay, and then on the other side, we need the initial speed that the ball moves up with. So that's Vi but Vi is the final speed for the total problem. So initially it hits the floor, that's why the Vf here is Vi, and then it leaves the floor, that's after, so that's the final speed, but it's the initial for this section. And also just a reminder that if the ball goes to a height of 0.7 meters, that means after 0.7 meters, which is Vf, the speed is 0, so it stops. Okay, so we need to choose a direction of motion. Let's choose down as positive. If we choose down as positive, g is equal to positive 9.8 meters per square seconds. Okay, so now let's use equations of motion for this half to find Vf. So we know Vi, we know h, and we want to find Vf, we know g. Okay, so there's no t, then the equation of motion that we use is Vf squared equals Vi squared. So I'm looking for section 1, so problem number 1, plus 2gh. Okay, so and then we said Vi is 0, so that's 0, and we are looking for Vf, so Vf is just 2gh, and if we just plug in the values, it's 2, g is 9.8, it's positive because it's going down, so it's positive, and then h is also positive because the displacement is in the direction of motion, and it's just 1.2. Okay, so let's plug that in. So we've got 2 times 9.8 times, now we need 1.2. Okay, so we get the answer, and then just remember that that is v squared, so we need the square root of the answer, and that would be our final answer. So when you've got an answer like this in your calculator, just press the SD button, so it changes a fraction into a decimal, so that's the decimal, and we find 4.85. Okay, so because Vf is down, it takes the positive, so Vf will then be plus 4.8. Okay, let's just switch. So I just want to remind you, because Vf for this portion is down, it takes the positive, and Vf here would then be plus 4.8, and the next value is 5 meters per second. But just a reminder that Vf is actually the initial speed for the change in momentum. Okay, then now we are going to look at 2. So for 2, we know the final speed is 0, we know the height is 0.7, we know g, we want the initial speed. So again we use Vf squared equals Vi squared plus 2gh. Okay, so in this case Vf is 0, so we have 0 equals, and then the initial speed is what we want, so Vi squared plus 2, so g is positive because it's going down. We said down is positive, so that's positive 9.8, but h is up, so it's negative. The displacement is in the opposite direction of our positive, so negative 0.7. Okay, so you might be worried how we're going to have a square root which is negative. Actually we won't, because if you take this to the other side, the negative becomes a positive. So now Vi, if you just plug it in, so just press on, and then you have 2 times 9.8 times 0.7, and you get that. That's Vi squared. You need the square root of the answer, and remember to press the button. Then it's gonna be 3.70. So we get Vi is equals to, and remember that Vi is going up, which is negative, so remember that. So Vi is equals to negative 3.7. Okay, so negative 3.7 meters per second. Okay, and again a reminder that the initial speed for the second part is the final for the whole problem. Okay, so what is the change in momentum? Change in momentum, which is the impulse now, will be the momentum, so the final momentum minus the initial momentum. Okay, so what is this equal to? The mass of the object is given, it's 0.5, so the mass of the ball is 0.5 kilograms, so multiplied by the final speed, and the final speed, just a reminder, is this one. So we have negative 3.7, so the sign is important because it's a vector, and then we have the minus from the equation, and the mass is still 0.5, and now the speed is the initial, which was a plus, so plus 4.85. Okay, so then what is our final answer? So now let's plug it in. So we have 0.5 multiplied by negative 3.7. So if you have negative, you use this negative and not this one. So times negative 3.7, close the bracket, and then this minus is for minusing, the sign in between, so, and then times 0.5, 0.5 times 4.87. Okay, so 85, and this was the positive, so I won't put a plus there, I'll just leave it as that, and the final answer is negative. So we get the impulse is negative, so we get the impulse equals negative 4.275 Newton second. So what does this mean? Remember that positive was down, so it means because we have a negative, it's up, so the final answer would be 4.275 Newton second upwards. Okay, so that's the change in momentum. Okay, I just want to point out that the answer in your book is incorrect. So just correct that. The correct answer is 4.275 Newton second, and it's upwards. Okay, so now let's move on. We are almost done to question 4. Let's actually skip question 4 and go straight to question 5. Okay, so question 5, also there's a mistake in the solution, especially the second equation. One of these two should be a minus, but we'll see how that comes about. So number 5, we have a hockey puck B, which rests on a smooth ice surface and is this should be struck by a second puck. Okay, A, which is originally traveling at 30 meters per second and deflected 30 degrees from its original direction. Then puck B acquires a velocity at 45 degrees relative to the original velocity of A. The two pucks have equal mass, and we need to write down the equations to determine the unknown velocities after division. Okay, so let's see what we have. Okay, a new page. So this is page 55, number 5. Okay, so page 55, number 5. What we have is so we have a puck which I'll draw as a box, puck B, and it just rests initially. Then another one, A, is actually moving at 30 meters per second, so 30 meters per second, and it hits this one and then they are deflected. But you can see from here that I'm drawing the side view, which is quite difficult to see, to bring in the angles. So I'm going to draw the top view. So imagine that is how it looks like. There's our A, and there's our B. So A is coming in at 30 meters per second, and remember that these two have equal masses. So this has mass M, that's mass M, that's mass M, and this one initially just rests. Okay, so what I'm going to do is I'm going to choose X, as I said earlier, as the direction of motion, and I'm going to choose Y as the perpendicular to that. Okay, so what happens afterwards? Afterwards we are told that this was the initial direction of motion for A, that one of them goes at an angle. So let's say that is A. A goes at an angle of 30 degrees. Let me just double check to make sure. Okay, so A is deflected at 30 degrees to the original direction, and B is deflected at 45 degrees. So it's similar to our pool example. Okay, so now let's call this speed VA, or velocity VA, and this velocity VB. Okay, so how do we solve this problem? We are going to use conservation of momentum in 2 dimensions. So let's start. So momentum before equals momentum after. Okay, so, and this is in the we start with the y direction because it's easier. Okay, and in the y direction you can see, so that is x and that's our y. You can see that initially there's no components over here, so 0 for A and it's 0 for B. Then afterwards for A, y is up, which is positive, so it's m, and then for the speed it's positive. The magnitude is VA. I want the y component, the angle is 30, so it's going to be VA sine 30 degrees. And then I've got plus from the equation. The mass is also m, but now the other one is going down, which is negative. The magnitude is VB, so negative VB, and the angle is 45, so sine 45. Okay, so taking this to the other side, I learn that m VA sine 30 equals m VB sine 45. Okay, so that's one of the equations. But if you like, you can leave the equation in this form, and you can see why I was saying the answer in the book is wrong, because we have a minus for one of them. Okay, and notice that this is not unique. You could have drawn your diagram so that, remember, that was the direction of motion, so that A actually is below, so the 30 is over there and the 45 is over there. So that's equally correct. Okay, so that's our first equation. And then our second equation, we just use conservation of momentum in the x direction. So momentum before in the x direction equals momentum after in the x direction. So before, the momentum in the x direction is just for A. So we've got, let's call this speed V naught. So it's mass of A, which is m, times the speed, which is V naught, and the speed is in the positive direction of x, so this is a plus, and plus this is resting. Initially B is resting, so plus 0 equals, then the momentum after for the x components for both. So you can see that the x component for A is that direction, the x component for B is that direction, which both are positive. Okay, so it's mass of B. Actually, let's start with A. Mass of A times the magnitude of the speed the magnitude of the velocity for A, multiplied by, now it's going to be cos. So for A the angle is 30, cos 30. Okay, and then plus the mass of B. It's also positive, so I should put a positive there. And then VB, cos the angle is 45, so 45 degrees. Okay, so our second equation, you can also see that the mass m cancels out, and remember that V naught is 30, so we learn that 30 equals VA. Cos 30 is square root 3 over 2. Cos 45 is square root 2 over 2, but I won't put them in, so VA cos 30 degrees plus VB cos 45 degrees. Okay, so that's our second equation, which is over here. Okay, so that completes the problem, which is question 5. Okay, question 5 and question 7 are the same problem, so I would advise you to do problem number 7 on your own, and the hint that I would give is call this direction your x direction. So the direction of motion initially for the rocket is x, and the other hint I would give is because just remember that they said the rocket suddenly breaks up into two pieces of equal mass. So call this one m, call that one m. So it breaks up into two equal masses, which is m and m. So going backwards, you can see that the total mass was m plus m, which is 2m. So you have 2m here, you have m there and m there. And then again, it's conservation of momentum in the x direction and conservation of momentum in the y directions. And then you will be able to solve V1 and V2. So just like here, if you check this equation, I can write, okay, here I should have cancelled the m's. I can write VA in terms of VB, and then by doing what? By dividing by sine 30. So then we would learn that VA equals VB sine 45 over sine 30. And then I would use this answer in the second equation. So where there's VA, I just substitute this number and I can solve for VB. After solving for VB, I then substitute back VB over here to find VA. And that's how you would find V1 and V2 for problem number 7. Okay, so now let's look at question number 6. So question number 6, we are told we have a half kg bullet of mass. So the half kg is the mass. It's fired horizontally, so there's the bullet. It's fired horizontally at a speed v naught, and which is 45 meters per second at a stationary wooden block. So the block is initially stationary and it has a mass of 10 kilograms. As soon as the bullet hits the block, it instantaneously stops. So that means they move together. As soon as the bullet hits the block, they start moving together. Okay, so you can imagine oops, okay, my mic just fell, so sorry about that. So you can imagine that what you have is something like this. There is the block, there is the bullet. The bullet comes, it hits the block. As soon as it hits the block, they are both stationary and they move together. Okay, so let me demonstrate that on the screen. So what I mean is that, so what you imagine is there's your block, there's your bullet coming in, and as soon as the bullet hits the block, so that's the bullet block system, they then move together with the same speed v. Okay, so you can see that the total mass of the two is the mass of the bullet plus the mass of the bullet, the block afterwards, okay, times the speed. So this looks similar to inelastic collision. In fact, I think it is. So let's see what the question is. So the question was okay, so the block with the embedded bullet slides along a horizontal surface with a coefficient of 0.125. Part A, we should determine the speed, the takeoff speed of the block with the embedded bullet. So for that, we'll use conservation of momentum. We know the momentum before, it's just this plus 0, and then after it's the momentum of the bullet block system. So we can find V. Then how far does the block go or slide before it comes to rest? For that part, we just use work and energy, because we know that all of the energy of the bullet block system is lost to the surface. Okay, so let's start with part A. So once again, page 55, number 6. So part A, the momentum before equals the momentum after. This is in one dimension, so there's no need for x and y. And then before is just the mass of the bullet, which I'll call small m. For the block, I'll use big M, times the speed of the bullet, which is v0. So call that direction. The direction of motion is positive. So here this is a plus, and then plus the block is just resting initially, so plus 0 equals after they move together. So the total mass is m plus m, and the speed is v. So we are looking for the velocity v. But now, just a reminder that afterwards they move in the same direction as the block, which is that way. So this is just plus, so I don't need the arrow. Okay, so what we find is v is just, I need to divide by this m plus m. So I find m v0 all over m plus big M. Okay, so if we substitute, remember m is a half, v0 is 45, and then m plus m, big M is 10, so half plus 10. Okay, so what does this give us? This will give us, let's see, so we have a half times 45 over 10.5, which is 10 plus a half. So what we get is 2.14. Okay, so our final answer is V is 2.14 meters per second. Okay, so what that means is the final speed of the, or the initial speed of the bullet and the block is equals to 2.14 meters per second in the direction that the bullet was moving. So here I'll just use east, so it's east. So the bullet was initially moving east, and the bullet block system also moved east. Okay, so that's conservation of momentum. And then now for part B, how far do they move? For that, we know that the frictional force times the distance, which is the distance of how far they move, times cos theta is equal to the change in kinetic energy. So here I'm using the Wac Energy Theorem. So Wac is force times distance times cos theta, and it's also equals to delta Ek. Okay, so from this side, frictional force is just mu k n, but for the block in the y direction, it's only the weight and the normal force that are acting. So n is just mg. So I'll just rub off the m and substitute mg. So mu kn, and then now we've got s, and the angle between, so remember that the frictional force, there's the block, frictional force is acting in that direction, the block is moving in that direction. So the angle between friction and displacement is this one here, which is 180 degrees. Cos of 180 degrees is just minus 1. So then I've got multiplied by minus 1. This is equal to kinetic energy. Remember that change is final minus initial. Finally, they stop, so it's 0. Then initially it's minus 1/2. And okay, so here, remember that the mass that I put here should be for the bullet and the block, so it's m plus big M. Okay, so even here it's m plus m. That's the kinetic energy of the system, and then multiplied by v squared, and this v squared is the initial speed we've just calculated over here. So the m plus m cancels on both sides. The minus 1 cancels that minus. So then what we are left with is that S equals, this side I've got VI squared over, there's a 2, so 2, then I need to divide by mu k and g, so 2 mu k g. Okay, and then substituting, remember that So remember that we said it's 2.14 for VI, so 2.14 squared over, I've got a 2, mu K is 0.125, and G is 9.8. Okay, so plugging these in, what do we find? We find the following. So we've got 2.14, so 2.14 squared times, there's nothing else. So at the bottom we have 2 times 0.125 multiplied by 9.8. Okay, so if you multiply those out, you get 1.869 meters. Okay, so S is just 1.869 meters. Okay, so that's the two solutions. The speed was 2.14 and S is 1.869 meters. Okay, so that completes today's lesson. What I would then advise is that you check Blackboard. I will put a solution for number 3, which is a tedious question from page 54. So page 54, from the problems that you do with the lecturers, number 3 is a long question and it's elastic collision. So we use a combination of conservation of kinetic energy and conservation of momentum. My solution, which you can see over here, is a very long solution. Okay, so kinetic energy is conserved and momentum is conserved. So what you have initially is ball A is moving at 0.4 meters per second towards ball B, which is just resting, and they want to know how do they move afterwards, and that's my solution. But how do we get that? We start off and we look at momentum before and momentum after, and it's just one dimension. So before, only A is moving, and it's moving in what I've called the positive direction, which is the direction of A. So I've got the mass of A multiplied by the speed of A, which is positive, plus 0 because B is resting, and then equals the mass of A times the speed of A plus mass of B times the speed of B. That's after the collision. Okay, so if I substitute now, there's the mass, there's the mass. I don't know the velocities, so I leave them as vectors. Then here you can see there's a common 0, 1.5 and even there, so I just divide by 0.015 because it's a small number and it can be irritating working with them. So here I'll be left with 0.4. Then I only have a VA plus 3 because that's 45, this is 15. So dividing this by 0.015, you get 3. And from this you can see that I can write VA in terms of VB. So it's just 0.4 minus 3 VB. Then now we use conservation of kinetic energy. Kinetic energy before is kinetic energy after. Before is just A that is moving with a speed of 0.4, so it's just 1/2 ma v squared, and the 1/2s you can see also cancel. So and then B is just stationary, so plus 0, and afterwards it's just the kinetic energy of A and the kinetic energy of B. So I've just cancelled the halves, and then for A I've got the mass is 0.015. There is the initial speed, don't forget to square. For A after, I've got the mass. Then just remember that VA we've just found from conservation of momentum in terms of VB. So we want to solve them simultaneously. So substitute VA for VB so that you only have one unknown. Okay, so substituting 0.4 minus 3 VB. This is a scalar. We are talking about speed, so you lose the arrows. Okay, so you square that plus 0.045 and then times VB squared. And then just manipulating these two, you will find that the final answer for VB is 0 or 0.2. So 0 is when this is stationary, 0.2 is the final answer, which is positive. And then substituting the 0.2 in this equation, we get negative 0.2, which means A is moving in the opposite direction it came in. So that's how you solve the problem. But I will just scan this solution and email it to you. Okay, thank you for having me.